the final piece of the puzzle when we're trying to transport all of our knowledge from Rn to manifolds is figuring out how to integrate. So in this video, we'll use phi inverse and phi as in the second definition of a manifold. So basically the one where we've defined a manifold using parameterized open sets in the manifold. So recall that if I want to integrate over a single parameterized open set in a manifold, or a manifold parameterized by a single coordinate chart, we defined this a few weeks ago. It's if I want to integrate a differential form, I need to integrate over phi of u intersect m. So this I'm now thinking of phi, this is living in Rn. So I'm thinking of phi as the inverse of the parameterization of phi inverse pullback of alpha, where alpha is a k form on M, an n form on N, and M is an n manifold. So what if M isn't covered by a single coordinate chart? Or if M can be mostly covered by a single coordinate chart, but not completely. So this is the way we're going to deal with that. So suppose U1 through UL are open sets in M. UI intersect UJ is equal to the empty set if I is not equal to J, so they don't overlap. And the support of alpha is contained in the closure, the unions of the closures of the UIs. So the support of something alpha is the closure, not closure of the set where, so the closure of the set of all P and M such that alpha of P is not equal to 0. And if we have such a situation, so if the UI are the domains, or sorry, let's, because we're using the second definition, the UI are the ranges of the coordinate charts with sort of phi defined from some subset of Rn to UI, then I can compute the integral of alpha over M, and it's equal to the sum from I equals 1 to L of the integral over phi of UI of phi inverse pullback of alpha. And here, remember, phi of UI, U is a subset just of M. It's not a subset of the ambient larger Euclidean space, so this phi of UI makes sense. So I haven't actually defined what this is. But in any case, you can, this proposition is, I wanted to show this to you first because this is how we're actually going to integrate most forms over manifolds. The proof will sort of become clear once we define how to integrate forms in general. But this is how we're actually going to integrate most forms, because the actual definition of how to integrate a form in general is too complicated to use in practice. And one thing to note, so for a coordinate chart, we require phi to be smooth. So sometimes we have coordinate charts that are not sort of smooth all the way to the boundary. So for example, the coordinate charts defining the upper and lower hemispheres of a sphere are continuous to the boundary, but they involve a square root of like 1 minus x squared at the boundary. And so that's okay as well. So we can use phi that are a little bit more general than like exactly what we would require for coordinate charts, but in general, you want to be using phi that are coordinate charts. So why does this sort of left-hand side make sense in the first place? And then we'll explain that and then actually use this proposition to compute an integral. So to define what this integral is on the left-hand side, first we need to define something called a partition of unity. So for any covering, UI of M by open sets UI. So I'm I have my manifold M, and I'm taking a bunch of open sets that may overlap, may not overlap, but then something has to overlap to get the rest of M. So these are the UIs, so they're open sets covering M. A system of functions, psi I from M to R, with the support of psi I being contained in UI. So as above, this is the closure of all points in M where psi I is non-zero. And in particular, we said that the support is contained in UI, not just that psi I is defined from UI, because we want psi I to actually be supported in an open set. So that means the closure of the set where it's non-zero is contained in an open set, which is a stronger condition than just saying it's defined on this open set. And we want these psi i's to be smooth. And we want them to be valued between 0 and 1. And then we want their sum at any point to equal 1. For all points in the manifold. So if we have this, then we call psi I a partition of unity. And we say that it's subordinate to the open cover by the UIs. So it's a partition of unity because of this last condition. It partitions unity 1. And it allows us to sort of smoothly separate these open sets using functions. Partitions of unity are really helpful in topology in general, but for us, we're going to use it to define integration. So we define the integral of alpha over m to be the sum over I of the integral over ui of psi I times alpha. So this is just regular multiplication. And so this is just a new differential form. And this is going to, you can sort of convince yourself as an exercise that this makes sense if, for example, if m is just R2 even, and the UIs are just some open sets in R2, you can actually compute the left-hand side. You can maybe come up with some example where you can compute the right-hand side, or just convince yourself in general that these are actually the same thing. And then I guess one more thing, to prove the proposition here, essentially we have to, we can set the UIs to be these UIs and use psi I always equal to 1 because there's no overlap, so we never have any sort of complicated condition in this sum. And the reason why we can throw out, so the only issue is if maybe alpha is supported in the closure of this union, but not actually in the union of the UIs themselves. But this set is so small, it's a lower dimension than M is. So the integral of alpha over that set does not matter. And so I linked a chapter of Lee, or the proof of this proposition in this book by John Lee. And it essentially just goes back to like the fact that if you were integrating a function over R2, but the domain of integration was just a line, for example, you would get 0. So it's the same idea. Okay, but the reason why I gave you the proposition first is that this definition of actually integrating a function over manifold is really wild, and actually coming up with a partition of unity is pretty difficult. So as an example, we'll do an example of integrating using the proposition. Okay, so let's integrate the form alpha equals x dy wedge dz plus y dz wedge dx plus z dx wedge dy over S2 using the coordinate chart phi inverse of phi theta. Oh, actually, so this is not ideal. I'll use an f instead of a phi because I have a phi as one of my variables. So this is going to be sine phi cosine theta. So this is inspired by spherical coordinates. Sine phi sine theta cosine phi. as my parameterization. And I know that, oh, I guess, okay, sorry, one thing to say, so that I forgot earlier. This is if the phi inverses are orientation preserving, right? So the important thing is if they're not orientation preserving, I need to introduce negative signs, as I discussed, like exactly as I discussed in the integration video, video 23, I think. So I'll just write that down. If their orientation reversing, introduce a minus sign. Okay, so all right, so I'm integrating this 2 form over S2. So S2 looks like this. I'll put a little axes on here. So this is the x-axis, positive y, and positive z-axes. And this coordinate chart, F, covers almost all of S2, except it doesn't cover the North Pole, it doesn't cover the South Pole, and it doesn't cover this curve. I'll make it dotted, where theta is either 0 or 2 pi. As long as, if I'm using the domain theta phi are in the product of 0 pi and 0, 2 pi in R2. Okay, so F inverse is orientation preserving. So let's check this. So first I'm going to compute dF inverse. So that's cosine phi cosine theta, cosine phi sine theta, and negative sine theta. Negative sine phi. Then negative sine phi sine theta, sine phi cosine theta, and then 0. And how am I going to use this to show that F inverse is orientation preserving? Okay, so the first thing is I need to figure out what the orientation on S2 should be. So S2 is the boundary of the 3-ball, and I've already sort of written what a properly oriented basis should be by drawing the axes. This should be the first should be the vector that points in the direction of the x-axis, the second in the y direction, and the third in the z direction. So let's figure out what that means for orientations at this point here. I guess I didn't draw this sphere perfectly, but let's assume that this point is the image, the gray point is F inverse of pi over 2, pi over 2. So at this point, I want a basis for the tangent space to S2, where when I add the outward normal vector as the first vector, the other two vectors form a basis for the ball, the interior ball. So I'll just draw the other two vectors as the one that points in the x and the z direction, and then we'll just see how they should be oriented. So if I use the right hand rule, this should be 2 should be the one that points up, and 3 should be the one that points to the side. So that means that at this point, if I restrict down to just thinking of this point as a point in S2, not in all of R3, this should be the first vector, and this one should be the second vector. Okay, so that gives me the orientation on S2 at that point, and then I sort of continuously extend it. So what I need to check is that dF inverse sends an oriented basis in these phi theta coordinates to an oriented basis equivalent to this green one on S2. And I only need to check at one point because I know F inverse is continuous, so everything will extend continuously. So let's compute dF inverse of the vector 1, 0 at the point pi over 2, pi over 2. So this will be in the theta coordinates, I'm looking at pi, 2 pi, pi over 2. So basically, I'm looking at this blob here, and I'm taking the point Sorry, I shouldn't be at pi over 2. I should be at pi, not to scale. And I'm taking this point here and computing its image. The image of these vectors. Let's do it in red. These vectors, 1 and then 2. So this is my first one. If I compute at pi over 2, so if I'm taking the image of the vector 1, 0, I'm going to get the first column of df inverse, and I just plug in pi over 2, pi over 2. So cosine of pi over 2 is 0, so I get 0, 0, and negative 1. And df inverse of 0, 1 at pi over 2 is second column, so this is going to be negative 1, 0, 0. So this will be my second vector. So if I go back up here and plug in my first vector, it's 0, 0, minus 1. So it should point in that direction. And then my second vector is minus 1, 0, 0. Oh, and I forgot to add the points, but the points are going to be at, this will be at 0, 1, 0, which is where I'm drawing here. Second vector will be minus 1 in the x direction and then 0, 0. So it'll be pointing that way. So as you can see, if you sort of bend your mental state a little bit, you can rotate these red vectors so that they sit right on top of the green vectors. So that means that the change of basis matrix to change the reds to the greens is determinant, is positive determinant, and the orientations are the same. So here I'll just zoom in sort of on this blob. So what I end up getting, if I were sort of to be facing it head on, is this is 1, this is 2. And in my in the image of F inverse, I have 1 pointing down and 2 pointing to the right. So then if I were to just rotate everything, 2, 1, or, keep rotating, I'm going to actually get them sitting right on top of one another. And rotation is orientation preserving. Okay, so my orientations are correct. So now all I need to do is compute, compute, compute. So let's compute F inverse pullback of omega applied to d by d phi, d by d theta. So I'll do this kind of quickly because you've seen similar computations before. So this is just going to be omega applied to F inverse push forward applied to d by d phi, and then same thing, F inverse push forward applied to d by d theta. So this is going to be x, so I should write x in terms of phi and theta. So this is going to be sine phi cosine theta times dx wedge, dy wedge dz plus sine phi sine theta times dz wedge dx plus cosine phi times dx wedge dy, all applied to, this will be the first column, so cosine phi cosine theta d by dx plus cosine phi sine theta d by dy minus sine phi d by dz as the first entry, and then the second entry will be minus sine phi sine theta d by dx plus sine phi cosine theta d by dy. And then when I actually compute all this, I end up getting, it's not super hard, I end up getting sine phi. So what this tells me is that F inverse pullback of omega is equal to sine phi times d phi wedge d theta. And then when I integrate, so using my formula up here, so there's only one such ui, so there's no sum term to worry about. So the integral over S2 of omega, oh, I've been switching between alpha and omega. I'll just rename alpha as omega. When I'm integrating omega over S2, this is the same thing as the integral over 0 to pi cross 0 to 2 pi of f inverse pullback of omega, which is the double integral from 0 to 2 pi, 0 to pi, sine phi, d phi, d theta. And you can compute that this is 4 pi. So that's our example. One final thing to note as kind of a preview for Stokes' theorem. So if I take d omega, I can compute that this is just 3 dx wedge dy wedge d theta, wedge dz. And I know that the volume of the ball within the sphere, so this interior part, is 4/3 pi, because it's always 4/3 pi r cubed, but r here is 1. So the integral over the ball of d omega should be 3 times 4/3 pi, because d omega is just 3 times the volume form. So when I integrate it over anything, I should just get its volume. And that's 4 pi. So this is a little wild. The integral of over S2 of omega is equal to the integral over the ball of d omega. So I'll let you chew on that and end the video.